Okay, I want to take a look at question 5 from 2018. It's about Laplace transforms, so they give us some background about Laplace transforms. They remind us the definition of the Heaviside step function, because we're going to use that later on. And part A says use the time delay theorem to compute the inverse transform of that thing there, where A is greater than 0. So I'm going to remind myself what the time delay theorem is. And it's basically that if I've got e to the minus as times some function, and I want to do the inverse of it, the answer will be h of t minus a times f of t minus a. In other words, what would have been the inverse transform of this function, but I put t minus a instead of t, and I multiply the whole thing by h of t minus a, Heaviside function of t minus a. So I want the inverse transform of that. So I'm going to separate it out, and I'm going to say it's e to the minus as times by 1 over. Also, what I'm going to do here is I'm going to complete the square. S plus 2 squared plus 1. Okay, so why did I complete the square? Well, if you look at my table of transforms, I can see that if I've got something over s minus a squared plus that, the inverse transform will be e to the at sine omega t, and that's what I've got. I've got 1 on the top, I've got 1 there, so omega's 1. S minus a, well, I've got s plus 2, so a is negative 2. So my inverse transform, if it was just a normal transform, would be e to the minus 2t sine of t, sine of 1t. But because it's multiplied by e to the minus as, and I'm using the time delay theorem, I need to replace my t's with t minus a. So I'm going to get e to the minus 2 t minus a sine t minus a. And the other thing I've got to do with these is to multiply by h of t minus a. So that's my answer using the time delay theorem. If we look at part B, it says solve this differential equation using Laplace transforms. It's a second order differential equation. So I'll just y dash dash plus 4y dash plus 5y equals h of t minus 1 minus h of t minus 2. Y of 0 equals y dashed of 0 equals 0. So that's what we've been given. What I'm going to do is take Laplace transforms of both sides. And we learnt what the Laplace transform of y double dashed is. And it's s squared L of y minus sy of 0 minus y dashed of 0, and we derived that. So that's the Laplace transform of y double dash. Then I've got 4 times the Laplace transform of y dashed. And again, we derive this, it's pretty straightforward. It's s times L of y minus y of naught. So I've got 4 times that lot. And then I've got Laplace transform of 5y, which is the same as 5 times Laplace transform of y. So that's good. Now if you look in your tables, what's the Laplace transform of t minus 1? It's going to be e to the minus s over s. And the other one is going to be e to the minus 2s over s. So I've taken Laplace transforms of both sides, and I'm fairly happy with that. Everything is now in terms of L of y, instead of having all of these first and second derivatives. So y of naught and y dash of naught are both naught, so that's nothing, that's nothing, that's nothing. And I'm going to take my quadratic calculus. By the way, notice that that's the same quadratic we had in part A that we've done some work with already, so that's probably going to come in useful later on. Right, now the e to the minus s and e to the minus 2s, I think I'm going to be able to use those with the time delay theorem, so I'll leave those as they are. But that 1 over s I'm going to deal with. So I'm going to get e to the minus s minus e to the minus 2s. 1 over s squared plus 4s plus 5. So I've left those there because I'm thinking time delay theorem. I've put those together because I'm going to need to deal with that lone s, and I think the way to deal with that will be to use partial fractions. So the Laplace transform of y must equal that, and I've just taken out a fifth and I've multiplied this out. We can see that these two are going to be easy because they're just Heaviside function. These two, I've written the denominator like I did before, completed the square. If it was s plus 2 over s plus 2 squared plus 1, that would be just straight from e to the at cos omega t from the tables, but it's s plus 4, which is a bit of a pain. So let's just go to the side, and I'm going to call it s plus 2 plus 2. So it's going to be s plus 2 over s plus 2 squared plus 1 plus 2 over s plus 2 squared plus 1. And if we just take a quick look at the tables again, s plus 2 over s plus 2 squared plus 1 is going to be that, and 2 over s plus 2 squared plus 1 is going to be that. So I've got one of them and one of them. So this turns out to be e to the minus 2t cos t plus 2 e to the minus 2t sin t, just from the tables. and so I'm almost done now. So I know the inverse transform of those, they're just Heaviside functions. I've done the transform of that, and this is just the time shift that we did before. So I'm going to do the using A is 1 there, and the function is that, and then A is 2 there, and the function is the same thing. I'm pretty much ready to write the answer down now. So I'm going to inverse transform this whole thing. I've got a fifth. This one here is h of t minus 1. The other one's h of t minus 2. That's that done and that done. Minus. Okay, this one, I've got the transform here, and then I'm doing the time shift with A is 1. So it's going to be a bit of a mouthful. E to the minus 2 t minus 1 cos t minus 1 plus 2e to the minus 2 t minus 1 sine t minus 1 times by h of t minus 1. That's the time shift on that. And then it's plus, and then it's the time shift with A is 2 on the same thing. So it's plus e to the minus 2 t minus 2 cos t minus 2 plus 2e to the minus 2 t minus 2 sine t minus 2 h of t minus 2. I could simplify that a bit, but you got the idea. I'm just going to leave it as it is, and that's it.